Good morning. Welcome to our new webinar series on extreme events and hazards. I'm Margaret Boone, Program Manager with the Southern Climate Impacts Planning Program, and I will be the moderator for today's webinar. Rachel Riley, SCIPP Associate Program Manager, will be managing the webinar. This is the third in a series of webinars that will focus on extreme climate and weather events and hazards that affect the southern United States. Our last webinar focused on flash flooding. The topic of today's webinar will be severe weather. Today's webinar will feature a look at severe weather with the discussion of Waron Forecast Project, NOAA's Vision for Severe Weather Prediction by Dr. Wicker of the National Severe Storms Lab, and an overview of SPC operations and severe weather climatology by Dr. Patrick Marsh of the National Weather Service Storm Predication Center. I'd like to briefly discuss the goals of this webinar series. We plan these in order to provide timely and relevant preparation and mitigation information to our local, state, and regional organizations, agencies, and business officials who are directly affected by these various extreme events and hazards. Each webinar will include products and information useful for monitoring the hazard. We want to assure you that the information is seasonally relevant. You may ask questions or make comments at any time through typing in your chat box. We will address questions at the end of these presentations, and we will also put up a list of resources for you. At this time, I will now turn it over to Dr. Wicker.
Okay, well, good morning, everybody. Thanks for coming in. I'm the program manager, or the project manager. I always want to call it a program, but NOAA has all these little delineations. I'm a project manager for the Waron Forecast project here at the National Severe Storms Lab in Norman. And I'm going to try to give you an overview today. This is sort of a talk I've tried to make a little bit more accessible to general audiences. But if you find there's some terminology, I'll try not to use a lot of jargon. But if you find that there's some terminology, please type in the chat box. Please define that, and I'll answer it right away because I don't want to lose anybody. And I'm trying to keep in mind my audience, but it's a little fuzzy as to the technical level out there from everybody, and since I can't see your faces, I can't tell if I'm totally boring you. The Waron Forecast project was initiated about 3 years ago after about a decade of discussion in NOAA, and it's not just us. The reason why I have this first slide is to say there's just tons of people working on this. In many ways, the Center for Analysis and Predictions of Storms, CAPS at OU, has been working on this problem for over 20 years. And the goal really for NSSL is to sort of pull all the strings together from the various partnerships, whether it be on the operational side from the Storm Prediction Center, the Weather Service offices, or from our partners at OU or NCAR, the National Center for Atmospheric Research, et cetera, et cetera. So where our guy is to sort of organize the science, see what we can do with this project, which I'll explain what it is in a minute. It's a very ambitious project, and see how we can try to work towards transforming the warning process in the next 10 to 20 years. But it is really a sort of decade or longer type project. So let's talk about what the U.S. severe weather warning paradigm looks like now. And really in the last 10 or 15 years, it's really, I think, been transformed partly because of computer models, which have gotten pretty accurate, at least detecting sort of the big outbreaks, the big events several days in advance. And we tend to think of tornado or severe thunderstorm warnings as occurring, during the day and maybe over an hour period. But if you're really watching the weather and watching the news and watching the Weather Channel, you're now sort of getting information 2 and 3 days ahead of time. And what I'm trying to show here is sort of the Storm Prediction Center day 3 outlook, day 2, day 1. And what you see is that our computer forecasts of the environment, which is like, do we have a lot of instability and do we have a lot of vertical wind shear, have gotten good enough to have some confidence that we can say 3 days in advance there's going to be a big event. In this particular example I'm showing, it's a real example in the upper Midwest. And basically, you'll probably hear, at least in certain news areas and certainly in the Oklahoma City market, which is kind of an extreme example of weather awareness in some respects. People start talking about the weather event that's going to happen 2 or 3 days from now. And as you see, the confidence about where it's going to be and how intense it's going to be sort of increases as we get closer to the event. And then finally, on the day of the event, we go from a sort of high risk, I think is up there, to a tornado watch over the affected areas. And that means that you're supposed to be ready for tornadoes. And hopefully people pay attention to that, which is not always the case. And then the National Weather Service individual offices, like in this case in La Crosse, Wisconsin, or Madison, or Milwaukee, will be looking for indications of rotation in the storms. And basically then you end up with a warning at the end of this process for 45 to 50 minutes at the end of the whole sort of multi-day period. So this is, the idea here is that warnings are not just necessarily something that happens instantaneously or maybe associated with a watch. But, sorry, I get confused when I see people typing. Get distracted. I'm easily distracted, as anybody who knows me. So the idea here is that we're trying to we're moving very much towards the idea that weather warnings or severe event warnings are actually a multi-day process when they can be predicted, with some veracity, 2 or 3 days in advance. Not necessarily what town's going to be hit, but just what the general area is. So with that in mind, what is Waron Forecast? And in a sense, that's an example of Waron Forecast working there in a very gross way, because we sort of outlined the area where the action was going to be 2 and 3 days ahead of time. But when I speak of Waron Forecast, or the project I'm managing, is to try to use computer models to actually predict about an hour in advance what individual convective storms will look like. And the problem is that we really don't measure the atmosphere very well. And so we have a lot of uncertainty. And so what we really need to do is to use a whole set of forecasts of sort of the same event, sort of get our best guesses over a series of like 10 or 20 or even 50 sort of forecasts of these storms. And it's called an ensemble. And what we do with that ensemble is we try to grab all the data that's available from the surface, from radars, from aircraft measurements, and from satellite data to create, a sort of a guess at what the atmosphere looks like at 2 o'clock in the afternoon, and then try to predict it out for an hour. And the idea is that we're going to basically take weather prediction, which we don't do right now, and extend it all the way down to basically the scale of your neighborhood, about 1 kilometer, and try to do it over an hour period. And because we don't have a lot of certainty about what's exactly going on, because our data are limited, we're going to have to do it in a probabilistic way, much like you get your rain probabilities today. It's a 30% chance of rain, it's a 40% chance of rain. But the idea is that by adding probability to this forecast, to this warning, that hopefully we'll be able to tailor it in ways that will be more useful to the public. So why do we need Waron Forecast? Go ahead. Oh, great.
Oh no.
Maybe
Okay, well, I'll tell you what this blank slide, it's very interesting because I did this in PowerPoint usually.
yeah.
Okay, well, this is a slide that is supposed to tell you how warning lead times have changed over the last 30 years or so. And basically what the slide shows you is about in the last decade, since we've had sort of this completed development, that the Doppler radars were deployed in 92 completely and started being used all over the US, that basically our warning lead times have sort of flattened out to about 12 to 15 minutes. And that's happened over the last 7 or 8 years, and the statistics vary year to year around that number based on the number and the types of tornado outbreaks. The idea is that we basically have hit we're not going to get any farther just using the radar to extend warning lead times. And also, the other thing this thing shows you is that the false alarm ratio hasn't really changed very much. It has improved somewhat, but really it's pretty much flat for the last 20 years as well, where it's actually a fairly high. It's actually about 70%, which sounds really horrible, but it turns out that if you want to, it's very hard to decrease your false alarm ratio without decreasing also your probability of detection, i.e. actually catching the storms. The extreme example is that if you never want to have a false alarm, you never warn. Or the opposite of that is you warn on everything and you'll never miss an event. And so the false alarm, and people say, well, why do we have all these false alarms? Well, it's because we don't measure the atmosphere well enough, and we don't really understand what's going on out there very well, although that's what science is for. But sort of probability of detection and false alarm are really two sides of the same coin. They're really tied together. So getting one better, and it's really hard without changing the other one in a negative way. Next slide. So the deal is with Waron Forecast, or why we think we want to extend things out, is that we have events. We are, the United States is getting increasingly more dense population in fact, in cities. And we have these large-scale events, which eventually, unfortunately, I think we all know from watching things, something may happen. We have examples of football games, state fairs. I have no idea what's going on. Oh, I guess that's somebody taking shelter in the upper right hand. The lower left-hand picture is the Joplin, a shot from Joplin from 2011 near the hospital. A major boating event, NASCAR race. We get worried in the spring here when they bring the NASCAR races to north of Dallas-Fort Worth, especially because they usually do it right around the beginning of April, which is prime severe weather season. All these events require more than, let's say, 12 to 15 minutes of warning, because you have to basically move large amounts of people to shelter faster. And I think the other thing to sort of recognize here is that an individual's risk, i.e. what you as an individual need for a tornado warning, may be somewhat different than what somebody running a football game at OU or Colorado or at Iowa State or Texas. And you may be willing, as a manager of that facility or as the guy running the football game, to live with a little less certainty because you can't afford the risk. And so one of the things that Waron Forecast is sort of thinking about is we'll probably be able to give some estimate of severe weather probabilities out to an hour. But they may not be as certain as, let's say, today's tornadoes warnings. But that may be okay, because when you have to move 80,000 people indoors, you need an hour. And so we're trying to think about the problem, and we're also engaged with social scientists about how we are going to sort of manage people and how the response to this will be. And so it's really starting to think about, okay, we may not be any more certain. I shouldn't say that. We may or may not be more certain, but we may have a longer lead time with the same certainty. And so that, or maybe a little bit less. But if you're a hospital and have to call people in to move patients away from windows, that may be okay. And so the idea is that warnings are not going to be one size fit all anymore, that they're going to have this sort of variability based on your tolerance for risk. And so there's different sets of users and different sets of criteria for tornado warnings, for severe wind warnings, things like that. So we kind of already have probabilistic warning guidance. And if you think about the hurricane problem, and you look at that upper left picture there with the track of some hurricane, I think that might be even Sandy, okay? What you see is where the storm starts at the lower left, just off of Miami or east of Orlando there, or Jacksonville. And then basically with time, the warning envelope, the possibility where the storm might be somewhere in that, expands with time. And we're thinking about the same type of thing for tornado prediction. That is, to start off with a very certain, and it's going to go exact, it's going to go here, but with time you get more uncertain. And the idea is that you're supposed to pay attention not only to the center of the track, but also the edge of the track as well. And that's not, I think, even still explained very well, although people try to, in the hurricane problem, that really anywhere, even though you have this sort of center line to the track, the way the hurricane warnings is, it's really pretty much anywhere in that white area this hurricane would be expected. And then you can see sort of some extensions of that track where it did actually hit New Jersey later on last fall. So the idea here is that we already have sort of this probabilistics, although it's a very crude probabilistic way of showing the public hurricane tracks, and we're trying to do the same thing really for tornado warnings. Next slide, please. So, we're missing an opportunity. We really can probably do better than what we have. Next slide, please. So this is our vision, which has been around now for a while. And what you see in the lower left is a shot, a very classic shot. This is actually from a real data case from 8 May 2003, the so-called second Moore tornado, which we've now had the third Moore tornado, unfortunately, in the last 2 months. Okay. We have some dry line west of the Oklahoma City area. And what you see there is the actual radar image of some developing convection. And this environment actually on this day was thought to be very able to produce significant tornadoes. So I think we were under either moderate high risk down here. And the idea is that when these storms go up, our computer models will take the radar data and take all the other background data and try to run them out an hour and estimate where the storms, right now these storms are not mature. These are basically just embryonic storms or supercells. And the idea is that they would actually predict maybe that this thing will grow up into a mature rotating storm, and that blue swath that you see there with the darkest blue in the center would be a probabilistic forecast of where we think the best chance of severe weather would be in, let's say, over the next hour. And the white dashed lines are sort of giving you a timeline to follow in there, what time that swath is there. Next slide. And there you see what happens. About 30 minutes later, we have a mature supercell that's starting to produce a tornado in the west side of Moore, Oklahoma. And our computer model, which of course is perfect, will run that storm, will actually nail where the storm was. And the idea was that while the people in the dark blue were certainly should take notice, everybody in the outer shades of blue should also take notice, just like in the hurricane problem. Next slide, please. So this provides sort of instead of a big warning box, but more of a probabilistic way, a sort of probability way of predicting convection and what it might be. And we have basically two areas that we're working on. One is that when you have as many radars as we do now in the United States, we have tons of radars, not just from the National Weather Service. We have TV radars, we have FAA radars. We're very, there's no shortage of radars, at least in major metropolitan areas in the United States. And it's really hard to have the forecasters pay attention to multiple radars at the same time. In Oklahoma City, we have literally 5 radars that are actually government radars that people can look at any given time. So what people do now is the forecaster figures out which radar has the best angle and looks at the storm and gives them the best view, and he picks that one, sort of the radar du jour of the day, or the storm for that matter. What we're trying to do is actually, and I'll show you an example of this, is combine all those radars into a single sort of snapshot, a single picture of the storm. And then we're doing research to make that picture above, and that picture above is, I wouldn't call it science fiction, but it certainly is not reality yet, that we can actually do this in a, not only can we do it for a bunch of cases, but we can actually do it reliably all the time for forecasters, and that's the challenge. And that's really a lot of what we're focused on in the Waron Forecast project here at NSSL is it possible to make that picture happen? And the answer, frankly, the jury is still out on that. The Waron Forecast project is a 10-year research program funded by NOAA, hopefully 10 years. And we really aren't due to really make any significant decisions about whether we think we can move forward this until 2018. Next slide. So we have ideas, and we have these new techniques. We do have some analysis techniques, as I've mentioned. And where do we test these? And we test these in a very unique facility here at the NWC in Norman called the NOAA Hazardous Weather Test Bed, or the HWT. And basically, we bring forecasters from the offices, from the Storm Prediction Center, and we bring researchers together, and we basically throw them all in a room, and we force them to look at a lot of stuff and talk to each other. And the idea being that that there's not a lot, our jobs, we're all very busy people. Everybody everywhere is working very hard, and you are too. And basically, we don't talk to each other enough, is literally what it comes down to. So the HWT is a place for people who normally don't talk to each other, including from away from Norman. We bring people in from all over the country to get together and interact with forecasters and sort of really do this sort of back and forth, which is very good for both sides. As a scientist, I can tell you that I've learned a lot from being here in Norman, and I just came to the lab, back to the lab after being a student here in the 80s. And when I got back and started interacting with the Weather Service people and the storm prediction people, I have a much better appreciation of the problems and issues that they deal with than when I was sitting in my office in my university some years ago. And so I think this is a really great facility. And we bring these ideas from Waron Forecast to this, and we bring them to the experimental warning problem, the EWP mostly, and we go and we talk. We bring forecasters and show them stuff and say, is this useful? Because lots of times you can develop a lot of great ideas that you think are in the academic side and the research side, and you show it to the forecasters and they're going to go, I can't use that. It's not good enough. It's not what I need to see. It's not how I think about the problem. So if we go to the next slide. So here's what we can do already with sort of Waron Forecast like technology. As I said, we're going to create a snapshot, which we call a 3D VAR. We're going to use a technique called 3D VAR, which is just a fancy way of saying we're going to optimize, we're going to take all the observations and make the best guess of the atmosphere that we can. And we're going to basically create a local domain for forecasters to combine all those radars. Those little circles that you see are actually the radar, all the data we use from the radar is about 150-kilometer range. And we're going to combine them all together, and we're going to make a single snapshot of a thunderstorm, and we're going to show that to a forecaster and say, if you're going to make a warning, does this help? Next slide. And here's an example of one of these analyses. This is from a case in Colorado about, I don't know, 4 years ago. And what we're showing here is what the forecasters see in real time about 5 minutes after the radar takes the data is a single analysis from these radars, and the black circles are the rotations. That's actually what we call the mesocyclones. And you can see there's 2 mesocyclones in these storms. One, there's actually 3 at one point where these storms are sort of merging and integrating. And some of these mesocyclones are actually back up in the red. That's the colors are the radar reflectivity. I'm sorry I didn't explain that. That's how much rain's falling out of the sky. And the reds means it's really raining very hard. So the idea here is that we can actually take sort of create a 2-dimensional wind field and a snapshot, and then we just run together and you can see the animation. And animations often are very powerful for, as we all seen sort of radar animations, really powerful in terms of getting our brain basically processes all that information in a very nice way to sort of give us some sort of motion or evolution or some impression of what the trends are of this thing. So this is one example. We can do this now. We can't forecast off of this now fast enough because frankly our computers are not fast enough. But we can basically do this now and put this in front of forecasters, and we have, and what forecasters have told us, go ahead to the next slide, is that they really like it, which is good because it means we're doing something useful. Basically they feel that this is a very different way than what they're used to looking at. Because when they look at the radial velocity from a radar, you don't really have the full wind field. You just sort of have a guess of which way, if the wind's coming towards or away from the radar. So you sort of have half the picture in some respects. You don't have any information about whether the wind's blowing across the radar beam. And so basically our tests from this show that this is a useful thing. And so we actually anticipate working on this and growing this. And eventually this particular technique will probably be the first one to actually make maybe 5 or 10 minute forecasts in a couple of more years in the HWT. Next slide. But this pipe dream of making a 1-hour tornado forecast, which when I say that, I remember being a young scientist in the early 90s starting to study tornadoes. And I think if you'd asked me that I would be trying to predict tornadoes 25 years later or 20 years later, I would have looked at you and said you were crazy. I'm not sure how I got roped into this. I still think it might be a little crazy. But we're working on this HWT, or excuse me, we're working on the Wolf research. And I'll just sort of give you an overview of what we're trying to do with that. Next slide. So here's a very significant event that some of you may have heard of. It's Greensburg, Kansas from May in 2007. It was the first EF5 with the new rating system. It's a very devastating tornado that hit the Greensburg town, which is southeast of Dodge City, about 50 miles on the night of May 4th. And this storm is relatively close to the Dodge City radar, and it's a big tornado. And so our thinking was, well, if we can't do the big tornadoes with Waron Forecast, we probably aren't going to catch the little ones. So let's see if we can do the big ones first. And so next slide. So this is what a Waron Forecast in research mode looks like. You have some radar shots up in the upper left, but what I really want to bring your attention to is the plots on the right, and you see a forecast of the rotation. The purple are the contours of the radar from the model. And the sort of blue to red swaths are the probability of strong rotation. So the yellow is the actual tornado track, okay? So the yellow kind of goes northeast, and then actually the tornado does a curly Q just northwest of Greensburg as it sort of wraps up and dies. So what you see is that we have pretty much are able to make a 15, 30, maybe 45-minute forecast where we basically the highest probabilities are right along the observed track of the tornado. It's not perfect. Not all the members, remember I said we had to run 50 or 60 computer models on the same event, they were a little bit jiggled each, so they all give us a slightly different answer. So we sort of try to capture how certain we are about this event. And not all of them are showing up, but about 80% of them, at least in the first 30 minutes, have the track pretty well, although they have the track in the 15 to 30 minute range a little bit to the northwest of the actual track. And then as you go on in time towards 45 or 60 minutes, you basically, all the members are doing something different. In fact, some members have a new tornado trying to form to the east. That's what that little blue swath means, to the east of the tornado track. And the other ones have sort of the old tornado. So this is an example of what the research capability looks like right now. Next slide. And I'm sorry, can you go back? I forgot there was a. The idea there is that that's what a typical tornado warning would look like, the size of a tornado warning. So the idea here is that we may be able to drastically reduce the size of the tornado warning if we had a reliable, consistent system for Waron Forecast, so that we really wouldn't warn too many people needlessly. That would probably help with the perception that oh, I heard a tornado warning, nothing happened. Oh, I heard a tornado warning, nothing happened. It's not just false alarm. It's also some people may say they hear a tornado warning and don't really realize whether they're actually on the edge of the tornado warning or in the tornado warning. And so the idea is that we'd like to try to reduce the size of that tornado warning, at least by a factor of 2, I think, in the next 10 or 15 years. Next slide, please. This is another example, the same type of thing. This is from the May 8th, 2003 second Moore tornado. This is an F4 tornado. And you see the same type of thing. The reflectivity is contoured. There's a yellow line here depicting the tornado track. And our ensemble of storm forecasts are trying to predict the rotation. This one does pretty well for about 45 minutes, but it shows where the maximum track would be. Next slide. And again, there's our sort of typical tornado warning for that storm, which covers most of the storm. Next slide. So sort of finishing up or towards the end here. So we have lots of challenges here. This is a fairly technical slide, but we basically are trying to figure out how to do this. If it's actually, one of the biggest problems is that our radar data is not very good. Coming straight out of the radar, we have to fix a lot of things. How do we incorporate all the other data that we get from our observing systems like satellites? We don't know actually what's going on outside our door very well. That's the environment. And then how to deal with predictability of severe weather. Is severe weather very predictable? That's actually an open question about how predictable all these things are. And by that I mean, if you actually know what it is, if you actually had a really good estimate of what's going on now, how long before the butterfly effect essentially changes what actually might happen, or small scale, like, for example, with a tornado, how much disruption from going through a city would actually change your forecast and the flow at the base, and that might actually alter the storm. We don't have houses in our models right now or anything like that. We basically have flat ground and try to estimate the friction from whether it's trees or open land or things like that. And then there's a lot of stuff to do with that's really outside my area of expertise, and it will probably really need to be focused on in the latter half of this decade, which is really how to get people to take the right action at the right time and understanding why they act. It's not just a question of saying you should do this and us just sort of saying, hey, don't be silly or don't be stupid, do what we say. People make decisions for a reason. And what I'm learning from talking to social scientists is there's a very specific way of people interacting with their information and with each other to try to decide when to do what. And so it's actually a very complicated problem. In fact, probably in many respects as complicated as the science, sort of applied hard science side of this thing. And trying to understand how we can do better as as a government organization, as a service to the public, to actually try to get people to understand what we're telling them so that they can make the best decision for themselves and for their families. Next slide. And so a lot of things are changing. Communication has changed dramatically in the past 10 years. National Weather Service people are now using Twitter and social media, Facebook, to communicate to people. With cell phones, I think, are obviously going to be, I think you already get your warnings on your cell phones if you want them, and I think that that's certainly going to be the way of the future. But again, how you present the information and how you present the information in the context is going to be very important in how we do that. It can't be a 0 or 1 type of warning anymore in many respects, yes or no. But we're not that certain, and the atmosphere doesn't work that way perhaps either. Last, I'd like to do, next slide please. I'd like to talk a little bit about, other things showed up there. Well, anyway, so there's probably some interest about whether Waron Forecast ideas, if we had those implemented, might change the outcomes at the end of May in central Oklahoma. What I want to first point out is that both sets of tornadoes, we had 3 big tornado days. It's Sunday the 19th, 20 May, which is the Moore tornado, and then 31 May, the El Reno. Basically, all of these were exceptionally well warned by our Norman Weather Service office, who's just a fantastic office. And it's easy for me to say that because they are. It's just a really good office. There are a lot of other good offices, and just they really were on top of the situation the whole time here. And so people had warning. I'm not going to speak to whether everybody had great warnings or 20 minutes or 30 minutes or 5 minutes, but a lot of people had fairly good warning. And so why do we need Waron Forecast if the forecast officers are getting these events so well? Next slide, please. Well, as I said before, we probably can't beat 30 minutes of warning in these environments, but we can probably help reduce the size of the area warned, which means that less people will feel the need to do something drastic, for example, like what happened on May 31st with everyone leaving their homes. We also hope to provide these longer lead times, perhaps with less certainty, but to the schools and to the hospitals, which clearly in the Moore case might have been helpful, at least in terms of preparing and having a little bit more time or a little bit more thought. An hour warning make a difference instead of 15 or 20 minutes. We also hope to reduce the false alarm rate, and that's very difficult to do, but if we can do that, I think that will also have people trust our warnings a little bit more. And finally, we hope, and I put question marks on the last 2 because those are really way out there. We may be able to estimate the intensity or the width of the actual storm or the tornadoes. And if we can do that, I think we can also get people to think about if you're on the edge of the track, it's not EF5 damage right on the edge of the track, right? The EF5 damage occurs in the center of the tornado. So if you have a fairly good estimate of where the tornado track is, you probably have a better estimate of your risk as to living or dying, or whether you should do something drastic or desperate or anything like that. If people are on the edge of the tracks, they certainly are probably able to survive in their homes a lot better than people who are in the center of a violent tornado track. And trying to get people to appreciate that is one thing, trying to forecast is entirely another, and it may just never happen in my lifetime. But we're certainly trying to at least estimate what those are from computer models. And frankly, we know the reason why we have high risk or moderate risk or slight risk is because the environment will support different intensities of tornadoes or severe weather. So it's not like we don't have any clue about what the intensity of the tornado is going to be. Next slide. So there's a lot of people working in a lot of different places on this problem. It's cutting edge. It's extremely exciting work to do. There's a lot of potential there. Trying to figure out what's really going to work out and not work out will take probably another 5 years or so. But I'm privileged to be here and to do this work and to lead a great team here at NSSL and interact with all our great people here at OU and other places around the country. And I'll be happy to answer any questions. And thank you for your attention.
Thank you so much, Luke. I think that's some fascinating information. I know everybody's going to be interested to see how the next 5 to 10 years plays out. I'd now like to turn it over to Patrick Marsh with the Storm Prediction Center.
Get a little closer to the microphone.
Here, go ahead.
So as Margaret mentioned, my name is Patrick Marsh. I work with the Storm Prediction Center. I'm relatively new at the Storm Prediction Center in an official sense, although I have worked with the National Severe Storms Laboratory and the Storm Prediction Center in the hazardous weather testbed, which Lou mentioned in his presentation. I've been affiliated with the hazardous weather testbed since 2008. So a little bit about the Storm Prediction Center. We're part of the National Weather Service. And so the National Weather Service has 122 local forecast offices. And here's a map of the local forecast offices for the continental United States. And so when a lot of people, when they are getting information from the National Weather Service, a lot of that information comes from the local forecast office. And in a local forecast office, there's usually about 12 meteorologists, and they work rotating shifts. So somebody's there 24, I believe 2 people are there 24 hours a day, 365 days a year. And these shifts are actually really busy. The National Weather Service is tasked with, in addition to producing forecasts for the general public, they also have warning responsibilities. They have to produce aviation forecasts. And so these shifts are actually, there's a lot of work that goes on behind the scenes. And no matter what office that you tend to work, because severe weather is such a localized event and doesn't happen everywhere every day. When you work in a local forecast office, you tend to have a limited severe weather experience, even if you work in what's considered an active office, such as here in central Oklahoma. And this is just because you work on a rotating shift. You may not be on shift when a severe weather event occurs, and you may only have a handful of severe weather events throughout the course of a year. So next slide. Here, now we'll bring in the Storm Prediction Center. And so the goal and one of the jobs of the Storm Prediction Center is to help the local office. We're not here to compete with the local office. We're not here to overshadow the local office. We're here to lend our expertise with the local office. And so what we tend to do is we tend to focus on the severe storms. And as I mentioned, we're kind of a second set of eyes, if you will, on overseeing the larger severe weather threat. And what's crucial is, because we work in the Storm Prediction Center and we deal with this on a daily basis, we have a very high level of experience with severe thunderstorms. I believe I saw on average, it's somewhere in the neighborhood of about 10 years of experience on average per forecaster at the Storm Prediction Center. So obviously you have myself, who's relatively new. I don't have 10 years of experience working at the Storm Prediction Center, but we have other forecasters who have been here 20 plus years. It's very competitive to join the Storm Prediction Center. Part of that is because we have a very stable staff. When people get here, they don't want to leave. As a whole, the Storm Prediction Center values the responsibility that they have. It's a tough job looking out for severe weather, and we know that a lot of people's lives depend upon the quality of the forecast that we produce. And we accept that, and we appreciate the mission that we have, and we're dedicated to it. And so when a lot of people, for most people, when they come here, they don't leave until they retire. And again, I cannot stress enough that we are not here to compete with the local offices. We're here to provide guidance to the local office and guidance to essentially anyone who takes a look at our products. And along those lines, the Storm Prediction Center does not issue severe thunderstorm or tornado warnings. Those will always come from the local office, at least in the current setup of the National Weather Service. So a little bit more specific about the Storm Prediction Center. When we have a forecast shift, we have anywhere from 3 to 5 forecasters on shift at any given time. On any shift, we'll have a lead forecaster, and this is the shift supervisor. They're the ones who make the final calls on all the products that leave our office. So they'll read through the products, they'll make sure that they're of the highest quality, and when it meets the standard of the lead forecaster, it will be shipped out. The lead forecaster also has the responsibility for issuing the severe thunderstorm and tornado watches, and I'll speak a little bit more about that in the next slide. And generally speaking, the lead forecaster comes from the ranks of the mesoscale outlook forecasters. So they tend to be someone who has come from the Storm Prediction Center. So they have an idea of what is expected, how things work. And so another way of looking at this is the lead forecaster has an awful lot of experience. Now that's not necessarily always the case, but as far back as I can remember, the lead forecaster has always come from within the Storm Prediction Center. We also have 2 mesoscale forecasters. And in fact, the gentleman right in the forefront of this picture is a mesoscale forecaster. And the mesoscale forecasters are generally focusing on the 0 to 6 hour time frame. They're looking for areas in which severe thunderstorms may occur. In winter, they're also looking for areas in which convective snows may occur, or change over from rain to freezing rain, or freezing rain to snow, or any of those kinds of changeovers. And when the mesoscale forecaster identifies a region in which one of these phenomenon or severe weather may be occurring, or may be imminent, or is likely to occur in the next few hours, they write a mesoscale discussion that basically talks about what's going on, why we're concerned about it, and this is kind of a heads up. So this is kind of the pre-watch information that'll go out. We also have an outlook forecaster, and the outlook forecaster tends to focus on the longer ranges. They issue convective forecasts or thunderstorm forecasts, including whether or not there'll be severe thunderstorms possible, anywhere from the current day out to day 8, depending on the shift. And they're the ones who actually write the convective outlooks that if you were to go to our webpage and you click on the severe weather outlook and you read that text, they're the ones who are responsible for that product. And again, even though that person is the one who writes the product, it has to go through the lead forecaster for final approval, so that we can assure that it's of the utmost quality. If we go back to some, not mentioned on here is we also have a fire weather forecaster, and the fire weather forecaster tends to work during the day, and they're responsible for identifying areas in which fire conditions may be likely. And part of the reason you may be wondering, why is the Storm Prediction Center focused on fire weather? Aren't they the Storm Prediction Center? Well, in the western United States primarily, but sometimes in the plains, particularly in the West Texas Panhandle, the Texas Panhandle, and the western parts of Texas, you'll have what's known as dry thunderstorms. And these are essentially thunderstorms that develop because there's a lot of mid-level moisture and ascent and instability. And so we'll get these thunderstorms, but the low levels are so dry that very little rain reaches the ground. But because we have moisture still in the mid-levels, we generate lightning. And so the lightning strikes will strike the ground. And when you have really dry grounds, like when you're in a drought, which fortunately the recent rains may have abated the drought conditions, at least parts of Texas. But if we had not had those rains, we would be in an extreme drought for much of Texas. So you take this dry lightning strike, and it hits this dry ground, and chances are it's going to start a fire. And again, this is actually very common in the West. I've seen numbers rank that anywhere from around up to I think 11,000 fires on average a year are started by lightning strikes. So it's really important for us with our thunderstorm expertise to give guidance to the fire weather community about where we believe thunderstorms are possible, and we tend to highlight the dry thunderstorm areas so that fire crews can pre-position and know what they may be dealing with. So so it's not mentioned here, but we also have a fire weather forecaster. Oh, it kind of got squished here. The Storm Prediction Center has several products that we issue throughout the day. I mentioned we have the convective outlook, and we have the mesoscale discussions. We also issue the severe thunderstorm and tornado watches. And the severe thunderstorm and tornado watches are essentially our way of saying we believe that severe weather is essentially imminent, that it's going to happen in the next few hours if it's not already occurring. So this is the Storm Prediction Center's way of saying, hey, you need to be paying attention to severe weather. And in my personal opinion, this is the time in which you need to review your safety plans if you haven't already. Don't wait until the warning comes out, because the warning is more of a, hey, you need to act now. The watch is, hey, you need to pay attention. Something, severe weather is increasingly likely, and you need to know what to do should it be reported in your area. A couple other products that we issued, I mentioned that we have the fire weather products, and you can access those on our main page. But we also issue something that's known as the Enhanced Thunderstorm Outlook. So if you look at our convective outlooks, they tend to be for long periods of time, ranging anywhere from 24 hours on the day one time period, from 12Z in the morning until 12Z the next day. So that's essentially 7 a.m. Central Daylight Time to 7 a.m. Central Daylight Time. And then we update that throughout the day, but they always are valid from the initial issuance time until 7 a.m. Central Daylight Time the next day. So what the Enhanced Thunder tends to do is, although we're not specifying whether or not the storms will be severe, we try to break down when we expect thunderstorms to occur throughout the course of the day. And we tend to break this down into 4-hour periods so that you can kind of get a sense, are we expecting thunderstorms in your area early in the day, late in the day? Is it going to be an overnight event? And so we issue a probabilistic forecast of 10, 40, and 70% chance of thunderstorms occurring within these 4-hour blocks. So that's a brief overview of the Storm Prediction Center. If you have any questions about that, feel free to let me know. But real quickly, in the time we have remaining, I wanted to touch upon tornado climatologies, and I'm going to focus primarily on the southern climate zones. So hopefully that these are the areas in which you might be the most interested in. So what this figure is, it's the daily probability of at least one tornado occurring somewhere in the United States. And the data that I used for this are 1982 through 2011. So the blue dots are the daily probabilities, and then the green line is kind of the smooth probability to account for some of the variability. And so what you'll notice is starting at about February 1st through late December, we tend to have greater than a 20% probability of a tornado occurring somewhere in the United States. It really starts ramping up in the spring months. It peaks in early June, and then we taper off slowly through the rest of the summer. And then as we get into the cool season, October onwards, we really start to have a lower probability of a tornado occurring on any given day. And so I show this slide because most people, when they think about tornado season, this is the figure that they're focusing on. That tornado season really starts ramping up in late February, early March. It peaks in early summer, and then it declines slowly throughout the rest of the summer. Now, unfortunately, or fortunately, depending on your point of view, the United States is fairly large, and we have variability amongst the regions, so that the climate is not necessarily the same everywhere. And so the same holds true for tornado climatologies. The tornado climatology of various locations are not necessarily going to look like the U.S. tornado climatology. And so what I'm going to do now is I'm going to walk through some cities and show you the tornado climatologies for these cities so that you can get a sense of the variability, and that when we start talking about tornado risk, we can't think about this figure. We need to think about the local tornado climatology and the local tornado risks, because they are different. Even amongst the southern climate zone region, there is substantial variability. Next slide. So what I'm going to do is I'm going to start with Austin, Texas. And so this is the daily climatology, or the probability of a tornado occurring on any given day throughout the course of the year. So as you notice, because we're dealing with a really small area, excuse me, I should clarify that this is a probability of a tornado occurring within 25 miles of Austin. And so since we're dealing with a smaller area, the probabilities are much lower than if you were to look at the entire United States. But one of the things that I really wanted to point out is, you notice that there isn't really a dramatic peak for the city of Austin. It does seem to peak in mid-May rather than mid-June, which is for the U.S. And there's a minimum in the summer, but then you have this low probability that pretty much continues the rest of the year. So let's go a little bit farther north and look at Dallas. So if you look at Dallas, so I mean, essentially we're just going up the road by about 3 to 4 hours. If you look at Dallas, there is a fairly pronounced peak in early spring. And so it peaks around May 1st. And then we have a drop off on either side of that peak. And then you see this sort of secondary season in late October into early November, where there's kind of a secondary maximum in the probability of a tornado. So whereas the United States graph pretty much has a peak in the middle of the summer and it falls off from there, in Dallas, for example, you have an early season peak in the spring, and then you have a secondary peak in the fall. So let's continue going up I-35 and head up to Oklahoma City, and the peak is even more dramatic, where you start in mid-May, the maximum in tornado probabilities, and then you fall off as we move into June and July. And then there's a secondary peak of the season starting in late September or September in through mid-November. And just a couple more sites in Oklahoma. I believe the next one is Enid. It's very similar to Oklahoma City, although there are some subtle differences. If we move, now we're going to move west a little bit toward Lubbock, and you can see a really pronounced peak centered essentially the last week of May, and then not much of a secondary season in the cool season. And this has to do with some of the geography of West Texas. It's a lot harder to get moisture back up into West Texas, or enough moisture for severe thunderstorms in the cool season. Next one I believe is Amarillo, and it's very similar to Lubbock. So now that we kind of stayed in the I-35 corridor and the Texas corridor, and the signal seems to be very similar amongst themselves, in that there's a big peak in the spring and maybe a secondary peak in the fall. So now let's start to head east and see how the probabilities might change. So here's Tulsa. You notice that the probabilities in the cool season tend to be a little bit higher than we saw along the I-35 corridor. But again, primarily we have this peak in the spring. If we go to the next one, we have Fayetteville, Arkansas. Again, we have a little bit broader of a peak in the spring. It's not as sharp, but we also have a broader probability of having severe weather in the cool season. And this time, instead of it peaking in October, it tends to peak in November. Drop a little bit south of Fayetteville. Here's Fort Smith. Very similar to Fayetteville, although the spring peak seems to be a little bit lower than for Fayetteville, and points west. Drop a little bit farther south. Let's take a look at Shreveport. Here's where we start to see some interesting things, whereas the springtime peak isn't as high as we saw with parts of Oklahoma and Texas. But what's really important here is the fall season, the late spring, or excuse me, the late fall into early winter season really starts to pick up, and it's a lot higher than we saw for portions of the Southern Plains. Continuing to head east, here's Little Rock. Again, the spring peak is coming down a little bit, but what you're seeing is The winter peak tends to last longer, and it kind of feeds right into the spring peak. So while there is a maximum in late November, it doesn't decrease all that much from late November into early January, and then we pick right up into the spring season. Continuing to head east, here's Memphis. You kind of see the same kind of pattern. Heading farther east, here's Birmingham. Here's Nashville. And as you head into Nashville, the spring peak is a little bit lower and more broad. And if you look at the blue dots, you can see a lot more of the variability in the spring and the cool season. But then if you go a little bit farther south to Jackson, Mississippi, you'll notice that the spring season and the cool season are about the same likelihood or probability of having a tornado on any given day. And this is really important because as I mentioned previously, people tend to think about the severe weather season as being primarily in the spring. But in the southeast, it's not just the spring. You have almost the same probability of seeing a tornado on any given day in November and December as you do as March and April. And so people might tend to let their guard down in the fall, thinking, oh, we're outside the peak tornado season. But in Jackson, Mississippi, this is essentially the peak tornado season. There are 2 of them. And so you have a longer duration of lower probabilities in the southeast. And so people tend to need to be on guard for longer. You go to the next slide. This one's outside the southern climate zones, but here's a probability for Birmingham, and you can once again you see this dual peak where they're almost of the same magnitude. Here's the next slide, shows Huntsville, followed by Atlanta. And then if we drop farther south, we can take a look at Baton Rouge. And if you look at Baton Rouge, you essentially have the same probability of a tornado almost all year. And so although it's not as high as in the spring as it was in the Southern Plains, and the maximum's not the same, you have to be on guard in Baton Rouge almost every day of the year. Because your tornado season lasts essentially 11.5 months. And so this is the kind of information that people need to be aware of, that their local climatology is not necessarily representative of the national climatology. And ultimately, weather is local. Tornadoes are local. So people will probably be more interested in knowing about their local climatology and when that they should be most on guard rather than looking at the entire national climatology. And so the last slide, I have a couple of links here. We have daily climatological maps on the Storm Prediction Center website. If you click on the main page, if you just go to the main page, if you scroll down to the bottom, we have that day's daily climatological probability of severe weather. Now keep in mind that that's a climatology. It doesn't necessarily represent our thoughts for that day. This is just based on the historical information. And then at the second link, we also have, you can kind of get like weekly loops throughout the course of the year. And if you go to my personal YouTube channel, I've actually uploaded animations of the daily climatology throughout the course of the year for various fields. So you can go here and you can click on the animation and watch how it evolves from the southeast in January. It basically evolves into the southern plains into the springs. Then it moves north into the northern plains for the summer. It collapses back down into the southern plains in August, September, and October, and then moves back towards the southeast as we move into November and December. So you can look at some more animations there. And with that, I'll take any questions. I didn't put my email address on here, but I'll leave it with Margaret so that anybody can, if you have more questions, feel free to send me an email, and I'm happy to try to answer questions. And if I can't answer them, I will hopefully be able to point you to someone who can.
Well, thank you, Patrick. I think those climatology graphs are just fascinating to see how variable it really is across the at least the southern plains and the southeast in comparison to the overall climatology of the U.S. So we will now open it up to any questions and comments if you have any posted. We will leave this list of resources up on the screen. And then all the presentation materials will be posted to our SCIPP website, as well as a 2-page summary that will be put together, and then that'll be emailed to everybody as well. This webinar is recording, and so it'll be posted to our SCIPP YouTube page and linked also on our Facebook page later, as well as sent out in an email to you all. We encourage you to continue to spread the word to make sure all those dealing with planning, preparation, and mitigation efforts of extreme events and hazards are involved with this webinar series. We encourage you to pass along our PDF summaries, our webinar announcements, our links to our YouTube videos to anybody that you think would find this information valuable. If there aren't any questions or comments, it doesn't look like there's any, then I just want to say thank you for your time today, and we look forward to continuing this conversation with you in the future. Thank you.